More than 2,000 years ago, Apollonius proposed this famous problem. Given any three circles, how can we construct another circle that is tangent to all three of them? To Apollonius, there are only a couple of tools we can use, a straight edge and a compass. A straight edge is like a ruler, but without any markings on it, so together with a pencil, we can draw straight lines but not measure any distances. A compass, on the other hand, allows you to draw a circle. For the purpose of this video, we are considering a non-collapsing compass, which means you can lift it off the paper, drag it somewhere else, and draw a circle with the same radius as before. So these are the only tools allowed when we proceed. This problem of Apollonius looks easy, but you can try it and see that it isn't a trivial geometry problem. In fact, we will have two simplifications. First, we want to only consider the case where the circles are in a so-called generic configuration, which means there are no intersections between any two circles and their interiors don't overlap. The other cases can be harder to tackle, and sometimes there isn't even a solution. The second simplification is that we only want to construct one circle tangent to the three given ones, because in general, there would be more than one solution to the problem, but we just want one of them for this video. Apollonius himself actually solved this problem, but his works were lost. But because this is such a famous problem, mathematicians developed different solutions to the problem. This video will cover one of these solutions, but the more important thing is the problem-solving technique demonstrated by the solution. This solution starts off with a powerful tool in Euclidean geometry called circle inversion. Suppose you have a circle and you want to invert this blue point with respect to the circle, then you will get another point. This point is not arbitrary and it fulfills two properties. Firstly, the image A' has to lie on the ray from the center to A. Secondly, the product of the distances from the center is the radius squared. If you invert a point twice with respect to the same circle, you get the same point back. This is because this property still holds, and so A is the inversion point of A'. One other thing to note is that inversion of a point can be done with straight edge and compasses. If you are wondering, here is one way to do the construction. We first draw a perpendicular from A to meet the circle at B, then draw a tangent to the circle at B. The reason it works is this pair of similar triangles, from which you can deduce this relationship between the distances. Something more interesting happens when you try to invert an entire circle with respect to another circle. This means that we pick a point on a circle we want to invert, then invert this particular point, and do this for every other point on the blue circle. You will get another circle. Here's the reason why. First, draw a line connecting the centers of the circles. You will then get two diametrically opposite points. Invert these 2 points separately, then we will use the following fact from Euclidean geometry. Whenever you have a circle with two diametrically opposite points, every other point will form a right angle with those 2 points. The logic works the other way too. If a point forms a right angle with 2 other points, then it must lie on the circle with those 2 points diametrically opposite to each other. With that said, we can use the definition of what A', B', C' are, which are the points A, B, and C under inversion. This will allow you to deduce the 2 pairs of similar triangles, and hence the right angle from C' to the images of A and B, which is enough to prove that the image is really a circle even after inversion. So far, we have established that the circle completely inside the yellow one will be inverted to another circle completely outside, and vice versa. If the circle crosses the circle of inversion, its image would still be a circle, and they both intersect the yellow circle at exactly the same 2 points. If, however, we are considering a circle that passes through the center of the yellow circle, then we will have a line instead. And of course, the line will invert to the circle. Again, we can use similar triangles to prove that the image is indeed a line, but more importantly, in all the cases that we have discussed, circles or lines are inverted to some other circles or lines. Because 3 points uniquely define a circle, 2 points for a line, we only need to invert at most 3 points to get the image under inversion. Since inversion of a point can be done with straight edge and compass, the inversion of 3 points certainly can be done, and so inversion of a line or circle can also be done. Sidetrack a little bit. Circles or lines mapping to circles or lines is just one interesting property of circle inversion. Another important property is that angles are preserved, but orientations are reversed. What this means is that if I want to invert this angle with respect to the circle, then we will get another angle. If we are measuring an angle between two curves, we take the angle between the tangents at the intersection. It turns out that angles don't change during inversion. But if we also assign a sense of orientation by saying that we measure angles counterclockwise, then after inversion, this angle will become a clockwise one, so orientation is reversed. This concept is called anti-conformal mapping, an important concept in complex analysis. Anyway, that's too much of a tangent. This is just to show that circle inversion is really important. Just one small point to note before we tackle the problem of Apollonius. If we expand all 3 given circles by exactly the same amount, then the yellow solution circle will be squished by the same amount. What I mean is that if we increase the radius of the 3 given circles by say 1 cm, then the solution circle will decrease in radius by 1 cm, and the centers of all circles are unchanged. This fact can be seen rather easily by joining the centers together, but this easy fact turns out to be very important. With all that said, let's get onto this problem of Apollonius. First off, we inflate all the 3 circles by the same amount until 2 of the circles touch at the point. We then use this point as a center to draw a circle. The radius can be arbitrary because we are treating this circle as the circle of inversion. Because these 2 circles pass through the center of the blue circle, when we invert everything with respect to the blue circle, the 2 circles on the top will be transformed into 2 lines. And the remaining circle just becomes another circle under inversion. Let's clear things up for a second. What we need to do now is to find the circle tangent to the 2 lines and the inverted circle. This is easy to do, because by being tangent to these 2 parallel lines, we already know that the solution circle has to lie on the middle line, and its radius being half the distance between the 2 green lines. Hence, we know the distance between the centers of the green circle and the yellow solution circle. We just need to construct a circle with that distance as the radius to see where the yellow center can be. I could have chosen the other point here as the center of the yellow circle and it would yield another solution, but I chose the bottom one for this video. After we have obtained the yellow circle, it's time to invert everything back with respect to the blue circle. The green lines and circles will be inverted back to the inflated circles, and the yellow circle will be inverted to yet another circle. But this inverted yellow circle is not any other circle. It is tangent to all the 3 inflated circles. Finally, we just deflate the 3 white circles and the solution circle will correspondingly inflate, and we have now obtained a solution to the original problem. All these might be a lot to take in, so let's take a deep breath and summarize what we are doing. The initial steps are transformations to the given circles. These transformations include, first of all, the expansion of the circles. Then we do an inversion, so that they become 2 parallel lines and another circle. Then we solve for the problem at hand, which is to construct a circle tangent to the green objects. After solving, we do all the previous transformations in reverse. So we first do the inversion, then we revert the expansion and do the shrinking of the white circles. So the yellow circle will correspondingly expand to become the solution circle. This demonstrates one very important problem-solving technique. If the problem at hand is really difficult, try transforming it into a simple problem to deal with. Then, instead of solving for the hard problem directly, we solve for the simple problem first. Then we do the inverse transformation to get the solution to the hard problem. In the case of Apollonius' problem, the transformation we did is a combination of expansion of the given circles and inversion. But the problem of Apollonius is not the only thing that can be dealt with this way. For example, an ordinary differential equation with a forcing term is generally difficult to solve, but if we take the Fourier transform, the problem becomes much easier. However, this is well outside the scope of this video. If you don't know yet, there is a Google form linked in the description which allows me to know your math levels and make the planning of future videos better. So please do fill in the form to help me create better videos. In any case, like, subscribe, hit the bell, and leave a comment if you enjoyed this video. See you next time. Bye.